Exercise 132 says, for each of the following pairs of compounds, identify the higher boiling point and justify your choice. So, liquid, let's say this is a molecule. Molecules will sometimes stick together, and the more they stick together, the harder it is for them to rip them apart. In order for them to turn into a gas or to boil, they need to be ripped apart. Gas molecules fly separately, one in one direction, another in another direction, whereas liquid molecules kind of stick with each other and roll around each other. And so to turn a liquid into a gas, you have to rip the molecules apart. And that becomes harder the more they stick together. In other words, the more molecules stick together, the harder it is to rip them apart, and the higher their boiling point will be. So when we're going to be comparing, when we're thinking about boiling points and which one is going to be higher and which one is going to be lower, we really want to look at how molecules stick together. What are the ways that molecules have of sticking together? Because that's going to determine how high their boiling point will be. Okay, the forces that make molecules stick together are called intermolecular forces. These are not things that happen inside of one molecule. They're things that happen between molecules. They're the stickiness between these molecules. There are three main intermolecular forces, and sometimes you may see these abbreviated as IMFs, intermolecular forces. There are three main ones that you would want to be familiar with. And from strongest to weakest, they are hydrogen bonds, dipole-dipole interactions, and London dispersion forces. Or if you've taken an anatomy class, or you intend to take an anatomy class, you might see these referred to as van der Waals. Van der Waals interactions. Just named after one of the scientists who discovered it and worked with it. So these are your three categories that you want to look at. These are the things that are going to tell you how much molecules are sticking together, and so how high their boiling points will be. So what are these, and how do you know if you have them? So first, let's think about hydrogen bonds. Now, if you have a water molecule, oxygen is really, really electronegative. So it pulls the electrons in these bonds toward itself. Being electronegative means you really are attractive to electrons. You attract electrons. And so the electrons go toward the oxygen and give a little bit of their charge to the oxygen. So the oxygen becomes a little bit negative. And since the electrons are going toward the oxygen, they're going away from the hydrogens, and so those hydrogens become slightly positive because they're losing a little bit of electrons around them. So carbon is a polar molecule. It has these slight positive and negative charges. Now if you have two water molecules and they come they brush past each other, and here let me just write these right side up. If these two molecules come together, how do they interact? Well, the the slightly negative charge on one oxygen is going to want to stick to the slightly positive charge on a hydrogen. And that attraction there is called a hydrogen bond. Now, that's a very misleading name because this is not a bond. This is actually, this attraction is around 30 times weaker than your average covalent bond. So it's much weaker than a covalent bond. It's not a bond, it is an intermolecular force. It is the strongest of the intermolecular forces, and it's used to hold things together like the two strands of DNA in the double helix. The two strands are held together by these hydrogen bonds. Now, maybe that makes sense. If in a water molecule, sure, this guy's telling me that it's a hydrogen bond. If somebody were to draw any molecule for you, though, how would you be able to tell whether that molecule has a hydrogen bond or not? You would have a hydrogen bond anytime you have really electronegative elements bonded to hydrogen. Not because there's a bond between them, that is not the hydrogen bond, but because anytime you have that happen, you'll get this separation between charges, and one charge on one molecule will be attracted to the opposite charge on another. So anytime you have nitrogen, oxygen, fluorine, or chlorine, if you look at the top of the periodic table, all of those elements are at the top right. They're all right here. Nitrogen, oxygen, fluorine, and chlorine. And that means they're really electronegative because electronegativity increases as you go up and to the right. So those elements all really attract electrons to themselves. Nitrogen, oxygen, fluorine, and chlorine. And if those are bonded to hydrogen, then you'll get these partial charges, and that will create an attraction between two molecules of that type. So that's how you know you'll have hydrogen bonds. Let's compare that with dipole-dipole interactions. I think that might give us some more insight into what a hydrogen bond is. So let's say you have a formaldehyde molecule. And formaldehyde looks like this. Now, you have an oxygen there, and oxygen is really electronegative, so it pulls the electrons to itself, becomes slightly negative, and the carbon that it's bonded to becomes slightly positive because it's losing those electrons. And what if you have two formaldehyde molecules and they brush past each other? What happens? Well, when they brush past each other, the slightly positive carbon on one will be attracted to the slightly negative oxygen on another, and that attraction is called a dipole-dipole interaction. First, a word about the name. If you look at this bond, you'll notice that it has two ends. It has a positive end and a negative end, so it has two ends. Positive end, negative end. Another way of saying two ends is dipole. A pole is an end, like the North and South Pole are the two ends of the Earth. And so that is a dipole. Now you have that dipole on that one molecule interacting with another dipole, a bond with two ends, on another molecule. So the interaction between these two dipoles is a dipole-dipole interaction. So that's where that name is coming from. And this is weaker than a hydrogen bond. So notice strongest to weakest, we're going down. Here dipole-dipole interactions are weaker than hydrogen bonds. And why? The reason why is because here oxygen is really electronegative and hydrogen has a low electronegativity, very low. And so what ends up happening is these partial charges end up being really big. They're almost full. So the negative charge on oxygen is really slightly negative, and the positive charges on the hydrogens are really slightly positive. These are really slightly positive. and the oxygen is really slightly negative. And so the attraction between these, because the charges are so large, the attraction is really big. In other words, the attraction is strong. Compare that with the dipole-dipole interactions. Here, you have carbon instead of hydrogen, carbon bonded to the oxygen. And carbon is more electronegative than hydrogen, which means when oxygen tries to pull the electrons to itself, the carbon pulls it back. And although the oxygen wins and gets a slight charge, the charge is smaller than on water. And the partial positive charge on carbon is smaller than the partial positive charge on hydrogen. And so the attraction between those charges is weaker because the charges are smaller. So that's one reason why dipole-dipole interactions are weaker than hydrogen bonds, because the partial charges are smaller, because the thing bonded to oxygen is more electronegative than hydrogen. And the other reason is because hydrogen is very exposed. Hydrogen is always on the it can only form one bond, and so it's always on the outside of a molecule. So it's very easy to reach. The hydrogen will have the bond, and all the rest of the atom is exposed to the world. It's like low-hanging fruit, and so this positive charge is very available to stick to that negative charge. Whereas if you look at the carbon on formaldehyde, it's kind of buried, it's kind of protected on three sides by the two hydrogens and the oxygen. So that's the second reason why dipole-dipole interactions are weaker than hydrogen bonds. Now the official difference between them, the rule of thumb that you could use to find out whether you have a dipole-dipole interaction, is that you'll have nitrogen, oxygen, fluorine, or chlorine, so those really electronegative elements that pull electrons toward themselves. But it won't be bonded to hydrogen. So it's bonded to something else. So notice here, it's bonded to carbon. You do have an oxygen, but it's not bonded to hydrogen, it's bonded to carbon. And that gives rise to these smaller dipoles that are harder to reach, and so that don't stick together as much, but don't create as strong of a stickiness between molecules. So dipole-dipole interactions. Okay, last but not least, let's think about our third and weakest intermolecular force, London dispersion forces. So London dispersion forces. Now if you have an atom, say this is an atom, you've got the nucleus in the center, the electrons are flying around. There's no guarantee, the electrons are flying around 4.5 million miles per hour, there's no guarantee that the electrons are going to be evenly spaced in the atom at any given time. As they fly around for a fraction of a second, most of the electrons could be, just by chance, on one side of the atom. And for that fraction of a second, all of the electrons and all of their charge will be on that one side, and so that side of the atom will be slightly negative, and the side where the electrons are not will be slightly positive. Now imagine that's not just happening to one atom, but to another atom right next to it. If that happens to two atoms that are right next to each other, the slightly negative charge on one is attracted to the slightly positive charge on the other, and that attraction between them, which is the weakest of the intermolecular forces, that is a London dispersion force. So it's really, really weak. And the reason it's weak is because these electrons keep flying around a split second later, and they're not arranged this way anymore, so you don't have those things, and the atoms don't stick together anymore. So you might even feel like that would be, if these are moving at 4.5 million miles per hour, this attraction would exist for so short a period of time that why are we even paying attention to it? But remember how epic of a period of time we exist on. 1 second to us is like over 219,000 years to an atom, so even if this attraction exists only the equivalent of once every 500 years, on our epic scale, where 1 second is longer than is the equivalent of 219,000 years, we would see lots and lots of little stickinesses adding together, averaging together as just a slight stickiness between the atoms. Now the key thing to remember with London dispersion forces is that they're more significant the more atoms come into contact. If you just have two atoms come into contact like we have here, right? If you just have these two atoms come into contact like we have here, then there's only one place where you could have that London dispersion force, the place that we drew. But imagine having, instead of just one, what if you had a molecule where these are bonded and these are bonded? Now, there are two places where you could get London dispersion forces. And if the carbon chain were even longer, so these were bonded and these were bonded, now there's three places where you could have London dispersion forces. And so the more atoms you have, the more they can line up. So like these are lining up, these are lining up, they come close to each other, the more places where you can have this London dispersion force. And so the more the molecules would stick together. One thing that interrupts this is when carbons branch. Because if you have these carbons here, or if you have these atoms here, if you have those atoms there, and there's a carbon coming out here, now that carbon is preventing these other atoms from coming into contact with the other group. So the principle you want to remember is that the more branching, the less the atoms come into contact with each other, the harder it is for them to all line up and come into contact with each other, so you have fewer London dispersion forces. And the molecules don't stick together as much. And if they don't stick together as much, it's easier to rip them apart and they have a lower boiling point. Okay, we spent a lot of time talking about theory behind this. Oh, I should note, London dispersion forces are in every atom all the time, or happening between all atoms all the time. The only difference will be how well molecules line up. So molecules with more atoms will have more atoms to line up, and so you'll get more London dispersion forces, and molecules with fewer branches line up better, and you get more London dispersion forces. So we've talked about a lot of theoretical stuff for a while now. Let's apply this to a problem and see how it works. In 132, they're asking you to identify the higher boiling point compound. And what they're thinking here is that you have a molecule like each of these, and if you had a population of them, which one would stick together better? And so you want to go down the list that we have here and check off each of these intermolecular forces. The one with this, and see which one has the stronger one. Now if they tie, then you would go to the next strongest intermolecular force. So let's just do the first one now, and then we'll continue with another one in another video. Okay, so here, let's start with this left molecule. In this left molecule, is this left molecule capable of forming hydrogen bonds to another version of itself, to another molecule like itself? So you'd want to see, does it have a nitrogen, oxygen, fluorine, or chlorine? It does. Is that bonded to hydrogen? It's not. It's bonded to two carbons. And so this will not have hydrogen bonding. This would not be able to have hydrogen bonding. How about Dipole-Dipole interactions? Does this molecule have nitrogen, oxygen, fluorine, or chlorine? It does. Does this molecule, is it not bonded to hydrogen. Yeah, that is the case. And so this molecule will have dipole-dipole interactions. So we have dipole-dipole. Okay. And last but not least, are there London dispersion forces? There are. There are because London dispersion forces are everywhere all the time. They're in all atoms. They're existing between all atoms all the time. But notice that there's a lot of branching here. There's carbons. These carbons are not just in a straight chain. They branch off of each other, as opposed to on the right, they kind of go in a straight line. So there's a lot of branching. So there are fewer London dispersion forces. So that sort of summarizes the intermolecular forces between several of those molecules. If you look at the molecule on the right, is this molecule capable of forming hydrogen bonds with other versions of itself? And it's not, because to form hydrogen bonds you need nitrogen, oxygen, fluorine, or chlorine, which we have, but it has to be bonded to hydrogen, and here this oxygen is bonded to 2 carbons. So there are no hydrogen bonds there. Are there dipole-dipole interactions? There are, because you have a nitrogen, oxygen, fluorine, or chlorine, and it's not bonded to hydrogen. It's bonded to 2 carbons on both sides. So this has dipole-dipole interactions. And when you have dipole-dipole interactions, you want to think about the number of atoms and the branching. Now, both of these two molecules have the same number of atoms. You have 6 carbons in both. So it's really just down to the branching. There's no branching here. Notice how this kind of goes in a straight line. You'd have a branch if a carbon came off one of these carbons. So there's no branching there. So there's no branching. And because of that, the molecules would line up much better, and there's more London dispersion forces. So when you're comparing these two molecules, you would notice that they both have dipole-dipole interactions, so those tie. But when you get to the London dispersion forces, this one on the left has fewer because of the branching, and the one on the right has more because there's no branching. And so the one with more intermolecular forces sticks together more. And if they stick together more, it's harder to rip them apart, which is what boiling is. And so you'd have to have a higher temperature or a higher boiling point. A higher temperature before the liquid molecules, which are all stuck together, get ripped apart. It'd be harder to rip them apart because they're sticking together with all of these London dispersion forces in this case. So we'll do more practice with these in a future video. I want to end this one because this is getting a little long. And I'll try to use visuals so you can see this a little better. But these are the ideas behind predicting relative boiling points. You want to look for the intermolecular forces, see which molecule has stronger or more intermolecular forces. That molecule will have the higher boiling point.